There we go. All right, so we were looking at this idea of partitioning variance as a really fundamental concept of what's happening here. So the distinction is that there's nothing that's being explained. All we're doing is carving all of the residual deviation off a predicted outcome and carving it up into pieces. So I would call U0 a random intercept. Some people would say, well, that's an individual difference, and I'd say it's still error, because I don't know why some people start out higher than others or start out lower than others. That's for the rest of the model to figure out. Likewise, I don't know why I'm off my mean today. So these are still conceptually unexplained variances. So let me show you how a multi-level modeler would describe that same exact model. A change in the notation. And I'll be honest with you, I sometimes write models this way when it's convenient, and I sometimes don't when it's not. So this is just another way of expressing the same set of estimated parameters and ideas with just a different notational system. So we start off with, first of all, contrasting what the level 1 model, as it's now going to be called, would look like for cross-sectional data versus longitudinal. So y sub I, if it's cross-sectional, switches to YTI, because I got per time per individual. Likewise, E sub I switches to ETI. But then we have this beta thing here. So beta across the old notation and the new notation is different. And I'm using red for model for the means and blue for model for the variance. And you'll note that beta is neither. Beta 0I, as it is now, is a placeholder. It is a collector. It's like a backpack. It holds stuff, but it's not a thing per se. Each person gets their own of beta 0, and what that's going to become is the intercept. So at level 2 then, this placeholder gets its own equation. And it is composed of a fixed effect in red and a random effect in blue. And because we're talking about intercepts, I would call this the fixed intercept and the random intercept respectively. They combine to create this beta 0I. So beta 0I is each person's mean conceptually, but it's broken down into what's the mean for everybody and how far off is yours. So this Y-looking thing here, this is gamma in my Segoe font. It looks like a Y-looking thing, it often does. And I have two subscripts here that will be more useful once we have more predictors to contrast them with. But it's 0, 0 because this is the starting point of both level 1 and level 2. If I know nothing else about a person or an occasion, I guess the grand mean. In multi-level data, this is not exactly the grand mean though. Once you have a random intercept with it, this is the mean of the person means. And that distinction matters if you have unbalanced data with different numbers of occasions per person. It's not the mean of the aggregated data, it's the mean of the person means. So when you look at output, for instance, from a multi-level modeling package, this will show up at level 2, even though conceptually it applies to all the observations because it's the mean of the person means. So the fixed effect, gamma 0, 0, plus the random effect combine to give me the beta, and then the beta comes back down here. So beta 0 is not a thing. It's just an organizational tool to hold things. Beta 0I is how each person gets their own intercept. So all told, there's only 3 things in the model. There's my fixed intercept in the model for the means. There's the variance across occasions and persons of the level 1 residual. That's one number. That's what the model assumes by default. And another separate number for level 2 variance across the random intercepts. So between person differences captured by U0I, within person differences over time captured by ETI. And if you don't like this placeholder notation, no worries, the composite equation is on the bottom right here. So it's just the 3 things. So this is what we would refer to as an empty means model because there's no predictors in it, and people would call this a random intercept model. So it's a 2-level random intercept model specifically, because I've got 2 levels of variability between persons and within persons. And this is always step 1. Because a logical precursor to doing a longitudinal analysis is that you actually have longitudinal information. Now, I know that sounds crazy, but I've seen it happen where you don't. So the very first thing that we want to know is how much information is due to each part. For those of you who are interested in sort of the mathematical underlying pieces of it, what's going to end up happening is that this model predicts a total pattern of variance and covariance across occasions that's known as something called compound symmetry. What this is saying is that hypothetically for 5 different outcomes from the same person, at each occasion, the total variability, say at time 1, is partly due to who's who, so intercept differences between persons, and partly due to when's when, time-specific E variation. And they add up together to be the whole variation at time 1. And this particular model says that holds no matter which time it is. The variance is the same across time, according to this model, because the only way people differ from each other is in their means. So once you factor in mean differences, there's no differential spread, they just go about their business. That's what this says. This may not be true. Likewise, the off diagonal, which is the relationship between time 1 and time 2, time 1 and time 3, time 2 and time 3, etc., is governed exclusively by the random intercept variance. Because this model is saying the only reason time 1 and time 2 is related is because this person's below average all the time, and once I factor that in, we're good. So this combined form is being built out of 2 separate pieces, the level 2 model for the variance and the level 1 model for the variance. Level 2 is what is referred to in software oftentimes as the G matrix, or what I call that SAS notation in particular. And all I have here is one random intercept variance, one source of individual differences. At level 1, I have this thing, which is known as a variance components or an independent structure, where I'm saying that the E variance is the same across time with no covariance. So after I adjust for person mean differences via my random intercept over here in G, the E's are unrelated with constant variance, just like we used to have in regression. So the idea of all of this is to extract all of these sources of extra variability and covariability until what you're left with is at the bottom is regression again. All the dependency due to person mean differences elsewhere. And for those of you who are skilled in matrix algebra and are looking at this and going, yeah, no way do you add these 2 things together and get this? I know. Here's the actual form. The G matrix gets pre and post multiplied by matrices that hold the number of occasions, so it's the right size to be added together. One important piece that we'll find in the output from this model, though, is a ratio. Of the total variability across occasions and persons, how much of it is due to persons? Of the total variability, how much of it is due to person mean differences specifically? How much of it is at level 2? How much of it is due to the random intercept? So that forms a statistic known as intraclass correlation. And if you're thinking, is this the same intraclass correlation I learned about in doing like inter-rater reliability? Yes. It's used in a lot of different contexts, but more generally an ICC is a ratio of variances of some kind. So those of you who've been through G theory probably look at this and say, this looks familiar because you can index relative agreement this way or absolute agreement this way with piles of variance in the numerator versus the denominator. This is your check as to whether you actually have longitudinal information. The intraclass correlation runs between 0 and 1. If it's 0, you have no person mean differences. If it's 1, all you have are person mean differences. So the second time that I taught a class on this topic at Penn State, back then I had everyone doing projects for every assignment. And I had a student in my class who was going to be the first person in his field to do a longitudinal analysis of blah, 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 and he got some data set. Homework number 1, make a picture of what your growth curves look like and calculate the ICC, and his was 0.99999, and his picture was as close to straight, parallel lines as I have ever seen. And so I asked to meet with him, and I'm like, dude, game over. Like, you don't have longitudinal data. Yes, I do. I have 5 occasions. No, you don't. They gave you the same answer each time. What you have is 1 occasion and 4 wastes of time. I wasn't quite that mean, but I'm trying to be emphatic. And this was late January, and I never saw him again after that conversation. He dropped. Can't blame him. And I felt bad about that, but then I thought, wait a minute, I'm not having this conversation with him at his final defense when he found out he didn't have any significant effects or even any variability with which to predict them, right? So if you don't have longitudinal information, game over. Like that's, and I've seen it happen. As long as you've got some information, you can play. So it could be 90-10, and at least you've got something to work with. But knowing how much is due to each kind is going to inform which type of predictors are going to be relatively more useful. If I know that it's 90% due to random intercept variance, then I know that differences between people are where the story is. I need predictors that differ between people. In contrast, if it's only 10% between and 90% within, then I know I need things that change over time to capture that information. So it's a precursor as well as a useful descriptive statistic. But it's only useful to some extent because this model assumes that people differ from each other only in one way, that the variability is the same across time, the covariability is the same across time, and those things are probably not true in longitudinal data. So it's a first step, but not the last step. Okay, questions? Good. Anything? Watching the chat too as well? All right. Then time slopes. So 2 potential questions that we would want to know about the effective time. So keep in mind that this could be occasion of measurement in a longer term study of change, or it could be day of the week, or it could be the change in cortisol after 30 minutes. Like time can be all sorts of different things. But the basic idea of what you might want to know about it is broken down into 2 parts. Is there an effective time on average? So is there any change on average? And if so, that's going to require fixed effects of time to describe what happens on average across people. And does that average effective time hold equally for everybody, or do people need their own version? And if they need their own, then we need a random effective time. So we can have either, both, or neither present in a given data set as a 2x2 combination. So let me give you some pictures, assuming just a linear effective time for simplicity. So I've got 4 pictures coming up here. The intercept is random in every picture. So this is beyond some people are higher or lower on average all the time. In what other ways might people differ from each other? Top left, panel A here. This is my depiction of a data set that would have no significant fixed effective time nor a significant random effective time. So the x-axis here is meant to be time. The y-axis would be whatever time-varying outcome you're trying to predict. The heavy black line would be the mean for the sample, and these are individual trajectories going through each individual point. So there might be like dots around the lines that are not shown here, so there is within-person variation as well. But if you drew a line through their data, it would be flat. So the picture shows no fixed effective time because the average line is flat. People are not changing. There's no random effective time because everybody's not changing the same. Question?
So is this kind of what you're saying with that other person, like you don't have longitudinal data?
Yeah, my poor student, this was his data set. Like this was the picture that he brought me. Like they told you the same thing 5 times. I'm sorry. It's not my fault. Yes, not only this picture, but also the dots where each person's observation would be were like perfectly predicted by this line. So I don't have the dots on here, but I could have. Like this could be a picture that shows all different types of within-person variation. We're just looking at what happens as a function of whatever time metric we're paying attention to here. Option B, yes, there's a fixed effective time, but not a random effect. So on average, people are changing, but they're all changing to the same extent. They don't need their own random slope. Question, can we measure the need for random effects via significant interaction terms between people and time? Conceptually, absolutely, that's what it is. A random time slope is the same thing as a person by time interaction. It is. That's how you can think about it. But it's a random effect and not a fixed effect, usually, in this case. If you made it a fixed effect, then you couldn't predict why some people changed faster than others. You just knew that they do. So if we look at the spread of the lines here, in both of these top pictures, the lines are parallel. That translates into an expectation that we would have the same amount of variance at any occasion and the same amount of covariance between occasions, regardless of which pair they are. This is the only situation in which the traditional univariate repeated measures ANOVA model is appropriate. Random intercept only, compound symmetry, equal variance and covariance over time. So no random in both of these pictures because everybody's individual line does not need to differ from the average line. Okay. Zoomers, how are we doing? With me? Thumbs up? We have a system of thumbs, by the way. Thumbs up for good, thumbs sideways for I'm not really sure about that, and down for, this is bad. So unfortunately, Zoom does not have thumbs sideways. That's how we talk to my son about his day when he's grumpy and he doesn't want to talk to us thumbs sideways. But I guess you could use the poop emoji for thumbs down. That would work. Or an angry face. I'll look for those. We'll figure it out. But most of them were up, so we're good to go. Okay, C, probably the most interesting scenario. Let's say that you have the misfortune of attempting a longitudinal study for your dissertation. So you spend all this time and energy collecting longitudinal data. You're trying to fix people, right? I'm looking at my psychology folks over here. You're going to do some clinical treatment. You're going to fix them. It's going to be excellent. And then you go home and you run your ANOVA because that's what you know how to do. And you have no main effective time. Wah, wah. And you might be sad. And then maybe you come to see me or someone else about it saying, is there anything I can do with this? And maybe you bring me a picture that looks like this and I get really excited. Because no, this is very interesting. On average, there's no change, but people are changing differently. Some are getting better and some are getting worse, which is canceling out on average. So now, why? Why did you make some people better and other people worse? That's the story. Then we get into things like personalized medicine or, intervention specificity kinds of stuff, right? Different slopes for different folks, as it were. Or you can have both. You can have change on average, but individual differences in the extent to which the change occurred. So practically speaking, just because you don't have a significant fixed effective time does not stop you from going on to look at the random effects, because it could be 0 on average because people are going up and down at the same time. So then the models that would correspond to each of these pictures were at A before. Empty means model doesn't even have time in it, so that is predicting a flat line. Doesn't have individual slopes in it, so that's predicting parallel flat lines. Let's get from A to B. In our multi-level modeling notation, I have picked up a new term at level 1 here, another beta placeholder, beta 1i, which in this case is just a linear effective time. So again, keeping it straightforward to start with, but time can be whatever it needs to be to make sense for you. So now because I have 2 different betas in level 1, I have 2 different level 2 equations, one for each. The beta 0 equation is the same as before. The only difference is what the fixed intercept means. Before, it was the mean of the person means because I had no predictors. Now, I have a predictor of time, so this is going to be the mean at time 0 specifically, what is predicted by a linear model of time to be at time 0. So not literally at time 0, but what's predicted. Over here on beta 1, I only have a fixed slope so far. This model predicts that everybody changes the same. So the effect that multiplies time is just this fixed effect right here. So we would say that the slope is fixed, meaning it's held constant across people and estimated to be one single number. So if I get rid of the placeholders and I write it just as a single equation, then the random intercept part is here, the slope part is here, but it's just a fixed slope. So this model would predict this picture B. It's allowing there to be some kind of linear change, but it's not yet allowing that linear change to differ randomly across people. Then the last piece, the random slope on slide 30 here, where my mouse is. Question: does something relate to heteroscedasticity of residuals? Does what relate to heteroscedasticity?
The graphic, letter D on the next slide.
Yes, it does. So people are spreading themselves out. So if you allow a random time slope, you are also simultaneously allowing the variance to change across time and the covariance to change across time. So you are introducing heteroscedasticity into the model, but not into the residuals, because they're separate, they're in E. So slide 30 here, we're picking up this new term in the beta 1 equation, U1. So it's another type of random effect. In this case, it is a random linear time slope, and it allows each person to have their own deviation from the fixed slope that's on average. And for those of you who are better with pictures, same. Let's have a picture. So slide 31 here, breaking this model into its pieces. Let's say that the black line here represents the average for the sample, and the blue line and the triangles represent one particular individual. Note the x-axis here is time starting at 0. So the idea of centering predictors so that 0 is meaningful, super important in these models. Not just in the presence of interaction, but always. Think of it this way. If I were back in my postdoc analyzing cognitive aging data, I routinely worked with samples of people from 80 to 100 years of age, in one particular study I'm thinking of. If I wanted to look at change as a function of age, but I forgot to center time, who is my intercept for? What kind of person would be my reference point for the model if I'm looking at the effect of age in very much older adults and I didn't center it?
Someone with age 0.
Age 0, I would be predicting cognition in newborns from data collected from super old adults, which is not technically wrong, but it's awfully weird. But where it gets into not just wrong, but potentially non-converging models is in trying to estimate the variability across newborns, the random intercept part. And I have seen models crap out. That's the technical term for non-convergence, when they just crap out on you and you don't get any answers, and it's like, I gave up, because it couldn't figure out what the variance of newborns was going to be. So I would want to fix it so that I subtract some constant so that 0 is within the scale of my data. Could be the mean age, could be the youngest person, could be anything, just somewhere so that it's in the data. Because the random intercept is going to refer to time 0 specifically once this random slope is here. Yes, sir?
What happens if your residuals or your errors are heteroscedastic? Like, you think that over time you'll have less variability or more variability within your error, like for each person? Is that?
So the question is, what if your errors are also heteroscedastic? So the introduction of this random linear time slope does allow some heteroscedasticity. It allows marginally, like overall put back together again, the variance to change across time. In addition to that, if you thought that people were becoming more internally inconsistent, like the E's around their line got more spread out over time, that's a location scale model. So I'm going to say this, and it's probably going to make our heads blow up. But conceptually, it would be a different kind of random intercept for the E's specifically. And it would capture individual variation of people who just fluctuate a little bit versus are all over the place. And you could allow the variability of the E's to differ across people randomly, to change over time. It could be whatever it needs to be. But a common misconception when people are fitting these sorts of models for the first time is that this E variance shouldn't be the same across time. By default, it actually should. Because if the E's have different variance across time, I would argue that the rest of your model isn't good enough yet. You're missing some random effects. So they could be scale model random effects, or they could be other functions of time, but your model is incomplete, I would argue. It is possible, of course, to let your E variance differ across time, but it's competing with what the random time slope's trying to do at the same time. It's trying to introduce heterogeneity too, so there's a redundancy there that's somewhat problematic. Okay. Other questions before we do the picture? Okay, so fixed intercept then gamma 0, 0, that's here. So it is the end of the line that is predicted on average from this linear model. Not what time zero's mean actually was, but what the model says it should be at the end of the line. Then my blue person, their random intercept, U0, would be -4, because that's the deviation from where the average is predicted to be by the fixed intercept. They're lower, theirs is negative. And for the same reason, it's where the line is predicted to end is the -4, not what they actually got. Because what's not on here is an E that would differentiate where they actually are from where their line ended. E is still in the story. Then we have our fixed slope. Rise over run, change in Y for unit change in X, to the best of my PowerPoint drawing ability, is about 6 on average. But my blue person started out lower, but they're coming back. They're growing faster than everybody else. So their random slope would be a +2 or so, because their total slope is 8. So the random slope is also a deviation, but it's a slope deviation. So a positive U in this context means they're changing faster than everybody else. A negative U would be they're changing not as fast. And the signs would work no matter which way the curve is going. So if I had people who are declining over time, is that right, Zoomers? I always get this backwards. This decline? Am I going the wrong way? Hang on. There. I think that's right. If we're declining over time, then somebody with a negative U would be declining more, because then their total slope would be more negative. And somebody who's not declining as much would have a positive U because they're less negative. So it can be any combination of up or down here, but the key idea is that everybody starts with a common slope, and then we get an offness to it. And we don't estimate the U1s directly, we estimate their variance across people. And so then, each person has their own line, but that's not good enough. E steps in to be whatever's left. So E is the deviation between the person's individual line created by their fixed and random effects and where their outcomes actually are. So this E is negative because they're lower than their line said they would be. This E would be negative, this would be 0, and this one would be positive. So if the line fits, then having the same E variance across time is a reasonable thing. But E is, why are you off your line today? I gave you your own line, that's not good enough. Consequently, to estimate this model, you need at least 3 occasions. If you only have 2, you can't do this. Because person by time and residual are not separable with only 2 occasions. You need at least 3. Coming along in terms of the estimated parameters that's not as easily shown in the scalar equations is a covariance. We also allow U0 and U1 to be related. How you start is related to how fast you change. And because they're describing the same person, you would expect them to be related. So that gives us 6 parameters in total. 2 U variances and their covariance at level 2, individual differences, 1 E variance that's assumed to be constant across people and occasions with no residual correlation, but those are testable assumptions. Okay. So are we okay with the concepts? Okay. So this model is saying then, conceptually, there are 2 different sources of dependency. People differ from each other in their level at time 0 and how fast they change. So where that shows up then is the same G matrix that we moved our random intercept to is going to hold our random slope with its covariance, and then level 1R is going to be this independence with constant variance thing. Now each of these we can change potentially, but this is sort of the default starting point for these models, is that you would assume that the only reason the E's were heterogeneous is because of the random effects that have been pulled out over here, and after we pull them out, then we've captured all the residual dependency and heteroscedasticity. That's all over here. All right. So then, contrasting intercepts and slopes. If everybody changes the same, if you have a model where the time slope is fixed, that predicts a compound symmetry structure, equal variance and equal covariance over time. Allowing individual differences in change as well as intercept creates a different type of structure, where particularly if it's a linear time slope, the model is saying that the variance is going to change in a quadratic U-shaped function around some minimum point. So the further away you get from the middle, the more spread out people are going to be. And you can figure out algebraically where this minimum variance place is. It's called an aperture, I think. So there's a word for it. But anyway, key idea is that at the same time you're allowing individual differences conceptually, you're also modeling dependency in a more reasonable way that allows variance and covariance to change over time. For those of you who like equations, here you go. This is from chapter 5 of my book. I put a link to the library, link to that. This is showing algebraically what happens when all of these things get put back together. And what I want to point to are 2 things. Number 1, the total put back together again matrix is complicated. But this is what it's built as for the variances and the covariances. This random slope model says that the total variability at any occasion is not just due to the random intercept, but it's also due to the random slope and which occasion it is. So there's a very particular form that is allowing us to predict for any occasion, not just the ones that we have in common, what the predicted variance would be. And likewise, what the predicted covariance would be. So it changes over time as a function of your random slopes. That's the key idea. What about people not cooperating? The good news is that by having variances change as a function, we don't have to have the same set of occasions. So if I have somebody who came in 4 occasions, this first little chunk of this matrix here, and they came in at time 0, 1, 2, 3, and I got someone else who only came in 3 times and they didn't come in when they were supposed to, so unbalanced data, no worries. The math still works and I still end up with a prediction for each of these people. So under the hood, what's happening is that each person is getting their own custom prediction as to what their variability and covariability would be like based on which occasions they have. So this works for unbalanced data or balanced data. You can't see the algebra as neatly with unbalanced data, but it's in there. And so then what's left over is an empirical question. You could test whether the E's still have some kind of relationship after factoring in the slopes. And for data sets with a lot of occasions, that's likely to be true. But the off diagonals here are all zeros for one very important reason. Can you guess what it is? Like this chunk is the data for person 1, and this chunk is the data for person 2. And this one here, and it's sideways in this one. The rest of these are just model parameters. Any guesses? This is saying that people are unrelated. The spots where we would have covariance across different people are all zeroed out because this model is saying that people are independent. Occasions are nested in people, but people are uncorrelated. Now, can that be wrong? Yeah, sure it can. If you have common students from the same teacher, or people who work at the same company, or spouses, they're going to have all their stuff be related to. So this is a two-level model that has the same assumption of independence at the top level that we're used to making. And if that's not true, we got to build in another layer of these random effects that then introduces correlation between different people in their use. Clustered longitudinal data, for instance. All right, enough matrices. So, big picture. Random intercept only. People differ from each other in their means, and that's it. Constant correlation and variance over time. At a random slope, people get to change differently, and the variability of your outcome changes as a function of what occasion it is, and so does the covariability. After accounting for the reasons why we have longitudinal dependency, these random effects are reasons for dependency, because some people start out higher and some people change faster. Those are reasons. After accounting for those, then the residuals should be uncorrelated with constant variance, or else you need to do something about that part of the model. So I have a foreshadowing here as to why I'm making such a big deal about this, is that one of the things we'll talk about towards the end of the week is longitudinal analyses done via structural equation models, where people don't talk about levels and they don't talk about random effects. And one of the most popular models, this idea of an autoregressive cross-lag model where last times X predicts this times Y, if you don't have the random effects in there, then those paths reflect at least three things. People starting out higher, people changing differently, and some occasions being worse than others. So which of those three things is responsible for those coefficients is meh, and that's a problem. But it's easy to fix it, fortunately. We just have to have this idea of person dependency represented as distinct sources of variance also present in those models. Yeah. So the total picture then of handling dependency looks like this. Summarizing where we've been up to this point. Once upon a time, there was an E. And that's all there was. But then we said, no, we can't do an E-only regression model on longitudinal data. That's crazy. So we split the E. We split the E into what we're calling within-person variation over time, because differences across time are going to be handled by the fixed effects, and between-person differences from each other in the random intercept. And if you add these two back together again, you're going to get pretty close to what the total originally was. Not exactly, depending on if you have the same number of occasions, but pretty close. But then from here, it's like, well, wait a minute. How are we going to let people differ from each other and change, too? Well, that's got to come out of this E. So at this point in the model, we can throw in a fixed effective time that allows the line to have a different slope, for instance. But then E is how far off your line. Well, what if you're off your line because it's the wrong fit for you? You need a different line. Okay, so what we're calling residual within-person variance is actually also between-person buried in there too. So the E variance in a random intercept model at level 1 splits into what is level 1 and level 2 again. So now, all told, the intercept variance stays for the ride. We end up with these three pieces. Residual variance is level 1. Why are you off your line today? I don't know. I got to have some kind of predictor that changes over time to explain that. Why do you start out differently at time 0, and why do you change differently subsequent to that? I don't know. I got to get some predictors for that. And I let these two things be correlated because they're both level 2. So what if you look at your E's and it looks like they still have some kind of differences in variance over time? Well, maybe it's because you fit a straight line and you need a bendy line instead. Bendy meaning nonlinear, quadratic, exponential, something like that. Well, you could fit another slope, for instance, a quadratic slope, which would explain some of the E variance, but then you could give each person their own quadratic slope as well. And then you'd be up to 3 different ways that people differ from each other, in their linear change and in their quadratic change and in where they start. So the way that dependency is being handled in mixed effects, multi-level, hierarchical linear models is by just pulling piles of variance out of it until what's left is all independent. So that's why the website for my textbook, the domain name is pilesofvariance.com. It was actually a birthday present from my husband, because that's what nerds give each other for birthdays, is domains. But that's been my shtick the whole time. It's like, no, these are just different piles. Like, and each pile is a different set of reasons, right? Why is it that? These are all conceptually different things. But under the hood, what's happening is that we're building in this really complicated prediction of what the E's look like when you put it all back together again. And the prediction is person and time specific. Whew. All right. So then in terms of the unconditional models of time, that's a word that means all we care about is time. We got to get this part right before we add predictors. If you're in the world of growth curve models, then we would want to make sure that our fixed effects are capturing whatever pattern of average change we have, linear, nonlinear, etc. Within person fluctuation models may not have any average effects, like something over here, but we would want to watch out for sort of the sneaky version of time, things that you don't think about in terms of day of the week or schedules and that kind of stuff. On the model for the variance side, if we're measuring within person change, then we're probably interested in individual differences. So all of our questions would be, okay, which of these aspects of my trajectory show individual differences and which don't? For fluctuation, though, it may not be the case that time is even in the model. So for this picture up here, do you think that adding a random time slope is going to do any good? No, they're not changing. Everybody, no change is the same. So a random time slope is not really accurate. But it's probably the case that occasions that were measured closer together in time are more related. So we might still want to find some way to allow the E's to be related that's not due to random slopes. So a common alternative for this would be introducing an autoregressive correlation for the E's after you put in a random intercept, for instance. It just needs to be there. It doesn't necessarily mean anything conceptually. If you wanted it to mean something, then instead of letting the residuals just be correlated, then you could get into the autoregressive kinds of stuff. So circling back to the reading speed and accuracy story. If you wanted to know to what extent does last occasion's performance predict this occasion's performance, then that can be your fixed effect. So that would be on average. And then are some people more impacted by last time's performance than other people? That's a random effect. So believe it or not, you can actually have a random autoregressive effect that varies across people. And that is heading into what is known as dynamic structural equation models. It's M+'s new thing, where they use Bayesian estimation to make all of that possible, but you can have random effects in residual predictive relationships like that. So you may need something like that instead for a fluctuation model.
So
right.
I have a question.
Please.
So I was just at a conference and there were a lot of EMA talks because I think that's like what's in vogue right now.
Sure.
But a lot of people brought up like the issue of measurement reactivity.
Mm-hmm.
And sort of as you were speaking, I was wondering if reactivity was something that we could just model out, like in the sense of like the random effects, like auto-regressive random effects for like within person fluctuation, or is that like does that logic work? Like I don't know. Like I guess I'm wondering about like those methods sort of worries and how they would fit into like this framework of modeling.
Okay, the Zoomers, did you hear the question? No, somebody did some done. Question was, in EMA studies, people are worried about reactivity to measurement, and can you model that somehow? And I guess, should you? Or my answer is I don't know, should you? Like, you need to see in your individual data set to what extent that looks like a problem. What I've seen people do is like throw out the first occasion, because the first time you fill out a questionnaire, you're going to do it differently than if you've seen the questions before. You could control for any difference of the first occasion versus subsequent occasions. If it was reactivity, like the stress example where you get off the phone faster if you say you don't have any stressors, then what day of study it is with some kind of like exponential curve through it might work for something like that. If it's a practice effect, like if these are tasks where you are getting better because you've done it more, then certainly that kind of exponential where you improve rapidly initially but then it kind of levels off can model that type of practice effect as it's known, reactivity in a different context. Yeah, I do think to the extent that the things that you're looking at in the data could be related to those processes, then we'd want to address those processes first before you look at the stuff you care about. But absolutely, you can have individual differences in the extent of those processes as well. Yep. All right, other questions? 11:16, everyone's hanging in there. I'm impressed. Thank you. And yes, if anyone has lost their will to live because they've been sitting here for 2 hours, I understand. No offense. That's why I'm recording. You know, I've been through lots and lots of classes and workshops, and if I had a dollar for every time I thought, you know, I would have had that if you could have just said it one more time, like, I would have enough money that I would never need to work again. But I'm still working, so clearly that didn't happen. That's part of the reasons for the recordings, is because sometimes it just takes more than one shot to get it in. And certainly the Snyders and Bosker book and all the other multi-level books on my shelf have been read many, many times, and I get something new out of it each time. So it's a lot. There's a lot here. So what about nonlinear? So I don't have time. I decided not to go into this too much because the idea was intensive repeated measures data typically are not concerned with longer term change. But all of these types of change models could be relevant for other types of time besides long term. So if your line needs to be bendy, here are some choices in what they're called. Polynomial functions is probably still the most common. Like if you enter time squared, that forms a quadratic relationship. Time cubed makes it cubic. These are best suited for time slopes that change directions. So a quadratic model is a U, right? What goes up must come down, and what goes down must come back up. So people use them to model change that levels off, but to varying degrees of sort of theoretical usefulness. Time is treated as continuous throughout is one thing about these models that makes them a little bit tricky to interpret. It's not that there's like a quadratic piece or a cubic piece. It's all the terms are working together to create this complex nonlinear function. For different pieces, that's piecewise. So let's see, Lisa earlier brought up the example of how many sessions do I need and what is the rate of improvement before 15 sessions versus 15 more? Anytime that you have something happened in the middle and now things are different, that lends itself to piecewise functions. They're known as linear splines. So multiple observation baselines, for instance, where you have a bunch of observations during a baseline period where nothing happens, and then you introduce some sort of treatment and collect a bunch of observations, and then you take it away and see if it goes back down. Those types of designs are very well suited for piecewise models. And the idea is that you're modeling the overall nonlinearity in chunks that correspond to differential experiences during each chunk. So I once had someone who was very excited about this idea, a developmental student, ask me, so can I have like a piecewise model of like before and after puberty? Sure you can. You just need a column in your data set with the date where puberty hit. And then it's fine. Then you got before and your after. Barring that, there are ways to estimate what that column would be, believe it or not. They're called latent knot point piecewise models, where one of the things you're trying to figure out is where the break should be in a continuous time, and potentially individual differences in where the break could be. So if you think about learning, some kids are going to pick stuff up faster than others. So initially, right, they might learn really quickly and then kind of level off. You may have individual differences in where the leveling off part starts. So that would be a piecewise model with a knot that's joining two lines together, essentially. So these are usually linear. They don't necessarily have to be. Linear effective log time. If you want to fit an exponential model the cheap and easy way, take your time variable in your data set and take the natural log of it. Put in a linear slope of log time, and that creates an exponential curve that starts to level off. And if you put in a quadratic effective log time, then you can control how quickly it levels off. That is preferable to truly exponential models that are nonlinear, because those are much harder to estimate with way fewer software options. Another one that I threw in here that I don't typically talk about in my classes, but that I think is very useful, is what's known as latent basis. So this is an SEM concept. I have a couple slides on that coming up later in the week, but briefly, the idea is that you let the model figure out what the function should look like. So it is in the context of estimating factor loadings for each specific occasion. You nail down the first one at 0 and the last one at 1, and you let the others all be estimated, and it describes what proportion of change has happened by each point. So it can be any kind of weird curvature or steps that's needed, and you can have individual differences in those functions as well as in the amount of change implied by a function. So latent basis is the key word for that one. There's probably 8 million other families that exist, but these are the ones that I found most useful to me. Any that I left out? Zoomers, can you think of any? Roomers?
Yeah. Like multivariate longitudinal data or so I have bivariate data, but you expect one to have one shape and the other data to have a different shape. So for example, like with accuracy, it's doubly bounded, right? You have 0% accuracy and 100%, and you're probably going to level off once you get close to 90-something%, right? Whereas words correct per minute, you might expect like maybe there's going to be more linear growth in that. And so can you do that separately?
Yes. So the question was, if I have outcomes that need different kinds of change, can I do each kind separately? Absolutely, you can. It gets a little tricky to interpret what relationships between each aspect of the trajectory would mean if they're referring to different concepts, but mathematically there's no reason. I would say with accuracy, though, that's an instance in which you may need to consider a generalized model version. In particular, something in the binomial family that would understand that accuracy can't go above 100 and can't go below 0, because otherwise your model would predict that accuracy like goes up to 120% if it's a standard sort of linear model without a link function.
So can you then combine a generalized model with a general model?
Yep. Yes, you can. If you can find software that will let you.
Okay.
That's the tricky part.
Can M plus do that? I mean, that's...
M plus does not have binomial. Stata does. But Stata doesn't handle missing data as well as M plus. So it's kind of like how you may have to go to like 6 different grocery stores to get all the specialty ingredients for an elaborate recipe because each store doesn't have everything you need. Software is a lot like that for these models. And yes, I'm talking about this sort of in one outcome at a time, but you can mix and match across outcomes and have some be certain kinds and some be others, whatever works most appropriately. All right. So big picture then, piles of variance, each predicted, each is a different reason why people differ from each other or occasions still differ from each other after controlling for which people it is. All right, 1124. So the next section here then is designed for folks who have seen structural equation modeling but are new to longitudinal and or new to multi-level. So if you're not someone who's seen SEM before and you're like, what the hell are these pictures? That's fine. It's fine. But I want to make the connection because a lot of times when people teach longitudinal, they do it another way instead. I prefer doing it in a multi-level framework because it builds on regression, and I feel like most people that's an easier place to start than SEM, which is a whole other set of words and pictures and notation. But nevertheless, here's the translation. So random effects, or what I refer to colloquially as piles of variance. By the way, do not write piles of variance in your manuscripts or your dissertations. The term is variance components. That's the correct way to talk about a pile. Random effects essentially represent person by predictor interaction terms. So a random intercept is like person by intercept, and a random linear slope is like person by time. So person by something interaction is the idea conceptually of a random slope. And their job is to capture patterns of dependency, different variances and covariances over time. But random effects are the same thing as what someone else might call a latent variable. So if you take any of the psychometric measurement modeling classes, we talk about latent variables as these sort of unobserved things we believe are there, but we can't measure them directly. So we can't get out a ruler or a scale and figure out someone's aptitude or their level of conservatism or their level of anxiety, that kind of stuff. So in this context, we can say, no. A random intercept is a latent propensity, and it's like the amount of this thing that you have, and a random slope is a propensity to change. And then we can hijack the SEM machinery to fit the exact same concepts. So let's start with an empty model and work our way through where we were. So this is how CFA models, structural equation models more generally, the measurement part is written. So in my other class, YIS is the subscripts because it's per item per subject. I used I for item in that case. And each individual item response from each subject is a function of a fixed intercept. A slope, this lambda thing is a slope, it's a factor loading, so a change in notation, times the latent factor. So the thing that is causing you to answer the items the way that you are is F. I don't use any of the squiggle Greek letters because I can't draw them reliably. So it's F for factor. And then E is what's left over. So in this way of talking about it, U is F. So what we would call a latent trait, a latent variable, a latent construct, factor score, true score, theta, did I forget any synonyms? That's a random effect. And the pattern of loadings, right here, the slopes, then define what kind of random effect it is. So let's start with an empty model. It would look like this for 4 occasions. So first off, you'll note I have 4 boxes here because this model is being estimated on a data set that's known as wide format, where each occasion is in a separate column in the data set. So it's 1 row per person in these models. Things in boxes are real, and things in circles are imaginary. So Y sub 1/4, these are 4 columns of data that I have. And I'm saying that I'm going to predict them. So note the arrows go from this red circle down into each box. I'm going to predict them with this level 2 intercept. And right now it's going to have a mean only, but not a variance, and that corresponds to this idea of a single level model, where all of the variability is in one term. We haven't split it up yet. All of the variability in these Y's is down here in their residual variances. So what we would have done is shut off the intercepts for each of the Y's so that their mean essentially moves up to the intercept circle. So there's no more information in the Y's. Their mean's up here, and then whatever difference from the mean they have and differences around the mean are down here. If we add in a random intercept, then that's the same thing as saying, no, this circle needs to have a variance to it. So a latent variable variance is the same thing as a random effect variance, and the mean of the latent factor is the same thing as the fixed effect. So the fact that the factor loadings here are all fixed to 1 means that this is an intercept. So this is a model that says everybody gets their own mean over time. That U variance is over here. Beyond that, at each occasion, there's some deviation from your predicted mean, and that's down here, and all of these would have equal variances according to this model. Okay, with me so far? So there's no time in here. Time is implicit in the subscripts of my y's. So I'm going to throw in another circle, fix its variance to 0 for now because this is a fixed linear time model. This is B over in the slides like an hour ago where I had A, B, C, D. This is B. Sorry, I'm watching the lights go on and off outside our room and thinking, are they trying to kick us out? Closing time. You don't have to go home, but you can't stay here. I have my new circle here, and I have fixed its loadings to define this circle as capturing linear change over time. So the first loading is fixed to 0 for this outcome, making this my reference for the intercept, and each of the subsequent loadings would keep track of how much time has passed. And if I estimate the variance of that latent variable, then we get to our full random linear time model where we left off. So this is the exact same thing as a random linear time slope multi-level model. It is the same thing. Put into the algebra that goes with it in terms of the predictions, what I refer to as the level 2 random intercept and slope variances and their covariance is up here in the G matrix. What I refer to as the residual level 1 variances is down here. And the Z matrix that controls each person's time observations is the loadings. So this brings us to our first, why wouldn't I do it this way? What if somebody came at time 2.5? Then what? If they showed up at time 2.5, I got to put their box either here or here and round it into 2 or 3. This is for balanced time. This is for everybody has the same 4 boxes at the same 4 occasions, not I came early or I came late. The extent to which you can fix that in SEM depends on whether your software you're using has something called a definition variable that allows you to customize what the loading would be for each person separately. M+, which is my preferred SEM software, has something called T-scores that allows this. I looked through all of the R Levon documentation and I could not find T-scores in R. Not to mean it isn't there, but that I couldn't find it and I gave up. Question, do the data need to be structured differently when moving from MLM to SEM? Yes, they do. So this structure implied by the picture is wide data, where each of these Y boxes is a separate column and it's 1 row per person. The multi-level modeling version of this is long data in which it's 1 row per occasion per person. So it's an easier way to think of this as 1 Y and 1 set of E's because it's literally from 1 column in the data set as opposed to however many occasions you have. So SEM is potentially problematic if you have unbalanced time, especially if you're going to have in time varying predictors. I've got resources I can show you about that. It's also potentially problematic when it comes to estimation. So there is no such thing as residual maximum likelihood in SEM software. Any of it doesn't exist. And I have some slides at the end here that I did not plan to go over, but it has details in it for those of you who are interested. The short answer is that regular flavor maximum likelihood results in random effect variances that are too small in small samples. REML solves that problem. The difference is whether or not the variances are adjusting for the number of fixed effects estimated like they do in regular regression. They don't in standard ML, and that makes the variances too small. If your variances are too small, your standard errors are too small. If your standard errors are too small, your p-values are too small. So if I did not have very many people, I would not do it this way for that reason alone. Why would I do it this way? Latent variables. No, I'm serious. Like if you had theta, or a factor that was measured by multiple items and you wanted to see if that factor changed over time, this is what you need. Everything in the standard multi-level modeling software is dealing with observed variables. So if you want to incorporate measurement models and see how your latent factor that stays latent changes over time. SEM is where you want to go. And not to make things worse, but I'll make things worse. There's also something now that is multi-level SEM, or MSEM, as it is abbreviated often. And the diagram that would go with an MSEM looks like this, because MSEM is back to stack data. So I have one column that is the time occasions, one column that's the outcome. I would still have my 2 random effects at level 2 and my level 1 residual for Y right here. So it's kind of just repackaging the same thing as multi-level. The big difference is that you can incorporate measurement models if you want to, and you can, where was I going with this? You cannot, let's go with that, use regular flavor, you cannot use REML. It's always regular flavor maximum likelihood. And so these models don't work well in small samples for the same reason. The version of this that allows autoregressive stuff, like the last occasion predicting the next occasion and individual differences, that's known as dynamic SEM, but it's estimated in MSEM. So then we get into the complete word salad of dynamic, multi-level structural equation models, which an hour ago was just, isn't this just regression with some random effects in it? Yes, it is. Yes, it is. So it's confusing to try and put all of the different words together, but it's really just one common set of ideas. Latent variables are random effects. Once you understand that connection, then how you estimate it has to do with your design, what you want to know, what else you want to do. Which store has all the stuff that you need? Maybe one store doesn't have it all, so you got to go to the one that fits best. And that's why I have a job, because then I can figure out which one is going to be least painful. All right, that's it. Yeah, words. So here's what I just said. I write things down so that I don't forget anything, and that you don't have to write things down. All right, details. That means I'm done. All right, questions or things that you want to talk about.
So is like the reason people like what's it called with their data like even with my data it's technically weekly, but that data could be collected on Monday or it could have been collected on Friday, and so what I did was I just made it so that everything was collected on Wednesday and I just rounded.
Yes. Okay. So he has unbalanced data where it could have been any day of the week, and we're just going to call it Wednesday.
Yeah.
So it's all the same. Okay.
Is that not what I should do?
Is that not what I should do is the question. As with everything, I would say, I don't know. It depends. It's an empirical question. So sort of theoretically, do you think that there's a difference in what the outcome being measured if you measure it at Friday of a week versus Monday of a week? Are they growing or changing that quickly?
I don't think so. I mean, I think there's just too much error to make a difference. I don't think you would notice, but yeah.
Do you think it's possible that kids don't want to do your stupid test on Monday because I hate school, which is the conversation we have at our house every Monday morning?
Yeah, or even Friday.
Or even Friday.
And I don't even know, like, did they do it in the beginning of the day or at the end of the day?
Yeah, beginning of the day or end of the day.
Or after lunch.
Yep. So you can treat your observations as sort of one long vector, and all these things we're talking about become predictors. Are Mondays different than Fridays? Is AM different than PM? Like these are all empirical questions. If you find that it does matter, but you don't want to care about it, like can I just call it Wednesday and just control for all this noise? Then you can parameterize your model to have what's known as an offset. Basically, you would put in another column as a predictor that's how far away from Wednesday you actually were, and then that goes in next to it. So it's a deviation slop factor that captures any differences relative to the other days of the week, but you'd have to get the right functional form for what the difference between days would look like. Otherwise, put in dummy codes. Put in a dummy code for what day of the week it was. So I think it depends on the context and the data, but ultimately, if you can phrase these deliberations as empirical questions and test it in the model, before you do any of the fancy stuff you care about, right? That like this part has to be right first. That's what I would recommend.
Okay.
And hope that it doesn't matter. Yeah. A lot of times people really have unbalanced data and they pretend it's balanced because it's way more convenient.
That's what I did.
It is. You have a lot more, you can just let the residuals be correlated. You don't even need random effects. You can use any kind of software you want. It's a lot more convenient, but it may not be true. So in the same way that you would never take a predictor variable and round it, you wouldn't want to round time into convenient bins and introduce error. But if you look at it and it doesn't matter, then maybe you can feel better about that. All right, what other questions? Zoomers? Anybody want to talk? Talk about their data? Talk about how this applies to them? Got Remmel versus Emil here otherwise. And significance testing and all that. And likelihood ratio tests, by the way, are how we decide what effects need to be random. That's a whole thing. And that's the end of that. Get out of the show. So you can all see each other again. Yeah, so this is like 2 hours, which in my fall class is probably 8 to 9 weeks of material, what we just went through, give or take. Because there's a lot of details that show up in the execution of these things, not to mention fighting with software. a lot of like the concepts are easy, but it's like, how do I make R do this is a whole nother thing. So I do have, on the Piles of Variance website for my book, I have examples for every single model in the book in SPSS, SAS, Stata, and in Plus. One of my eventual goals is to add R as a column, but I'm slowly working my way through all of the idiosyncrasies across R packages. So I'm not an R expert yet, but I'm married to one, which is very helpful in trying to figure out this stuff. All right. Do you want to be done?
Yeah.
Good enough, 11:42. If no one has questions for the group, I will hang out though, and I will talk to anybody who wants to talk to me. How's that? One last question. In a random linear time model, power at level 1 is more important than power at level 2. Power questions. So power depends on what you want to know. If you need to predict why some people change more than others, that's a people power issue. You need more people. If you want to get a better index of the form of change, you need more occasions. And if you want to do both at the same time, you need a lot of occasions and a lot of people. So if I had, say, 8 people and 30 occasions or something, that's great power for level 1, that's crap for level 2. So it's just going to constrain what I can do in that context. For these sorts of models, I usually do simulation to do power analyses. The canned G-power stuff is built for like repeated measures ANOVA, not stuff with random effects. And I do have resources I can share with anyone who's interested in doing simulation power analyses, but it's all in SAS and M+, because that's what I know how to do. So, but M+ is pretty easy to pick up. All right, then I will let everyone go as a group. Again, I will hang out if anyone wants to talk to me, either Zoomers or Roomers, and I hope to see folks tomorrow. Tomorrow I'll have examples. Stories and examples. That's what we're doing tomorrow. So thank you, everybody.